Good. So, welcome to this presentation, which I have called Asynchronous Servlet Processing with Hystrix-Servlet. My name is Einar Rosenvinge. I work for ASYNCHRONOUS, and what we do at ASYNCHRONOUS is that we provide digital signatures and authentication for our customers. We integrate with something between, I don't know, 20 and 40 various backend services. So, but we'll get back to that. So, first of all, this blah blah. Anything I say could be a lie, and you can't hold me responsible for it. So, so what's this? What problem are we solving today? So, this is an image of a train station, and it's not just any train station. It's a train station in India. So, it looks pretty crowded. You know how many people live in India? Any guesses? It's these days is about 1.3 billion. So if a train is cancelled or delayed, then obviously it gets pretty crowded in the train station. So let's just imagine that from this particular train station there are two lines. Okay, there is the good line. This is actually the new bullet train to Mumbai. It's always on time, perfect capacity, never a problem. And as you might have guessed, there is another line, which is the bad line. This is the train to New Delhi. That one is never on time. It's frequently cancelled, always delayed, always problematic. So imagine then that you are in the middle of this crowd, and you're going to New Delhi, the bad train. Quite obviously, you might have a problem. I mean, you might not get onto the train, and if you do get onto the train, you might fall off. But if you're in this crowd, and you're going on the good train, would you then have a problem? Yes? No? Well, in theory, no, because the train is always on time, right? So you can just get on the train and go. But I would say that you could also have a problem in that case, because you might not even be able to get onto the train, because the train station is so crowded, right? So, and I mean, Indians are very polite, so you can just tap on the shoulders and say, excuse me, but you would have to tap on a few thousand shoulders. So you would still have a problem, or could have a problem. So as you might have guessed, we're not going to talk about trains. So the train station is your application. And you have your users on the right-hand side, and things are flowing pretty nicely through your system. You are integrating towards a system A and a system B. Those are backends. They're not yours. Those are remote backends, not controlled by you. To make matters even worse, it could also be that the vendor of A or B has told you that to communicate with us, just use this library. We're giving it to you. Here it is. It's binary only. Just link with this. And you go ahead, you try it out, and okay, it works well. So requests are flowing. Look at this fancy animation. From your users through your system and to the various back-end services that you're integrating towards. But as you might have guessed, this system A is getting really slow. Just randomly, one day, it happens. It doesn't go down, but the latency is horrible. It goes from 100 milliseconds to 10 seconds. And what happens? Or what could happen, right? Well, it could be that the requests are piling up. So you are queuing requests towards A because A is not responding in time. And you have no proper timeout mechanisms towards A because the vendor of A just gave you this library. Use this to communicate with us. And you can't change that. So the requests are piling up, and all your threads are kept busy towards backend A, and no one can serve the requests that are only going towards B. You could, of course, argue that you could just separate these into two different applications. But there are reasons why you might not want to do that. Maybe there are users coming in that are actually going to use both A and B, or A and B and C, right? So one of the reasons this is the way it is the classic Java servlet paradigm. So the way it was before Servlet 3, right? It's one servlet container has a thread pool. Obviously, it needs to do several things at one time. So typically a few hundred threads. It's an entirely synchronous mode. And what does this mean? It means that each thread will read a request from the network. It will prepare a response object and hook everything up correctly. And then, in time, it will invoke your code. And your code is in servlet.service, right? So you have inherited from the servlet class. You're doing your thing in service. And whenever you return from service, then the thread is done, and it can serve the next request. Fine. But what happens if what you're doing in service takes a very long time? Well, quite obviously, all the threads might end up being blocked inside service, right? So this is just a very simple example. You see, on the first line of the body, we're getting a reference to a very slow service, just as an example. We're calling a method which is blocking and potentially very slow, giving it a parameter which returns a string sooner or later. Then we're setting the content type and just printing the string. Fine. So this was somewhat mitigated by the Servlet 3 API, where a servlet container could then hand over the execution of requests to a separate thread or pool of threads. And the servlet container thread would be ready to serve other requests. Okay, so let's see how that looks, okay? So in this example, I've just created an executor service, just declared it here. It's a simple fixed thread pool with 10 threads. So inside service now, I'm calling the request start async method, which returns an object for me to hold on to, an async context. And I'm just submitting that to this thread pool and returning from service. And when I do so, the container thread can move on and do other things. Now, obviously, inside this runnable, let's just have a look here as well. We can obtain the original request and response from the context. And we're doing the exact same thing, which we did previously. One important thing to know is, or see, is that we have to call context.complete, which basically tells the servlet container that we're done. We're not holding on to any of these references anymore. You finish up, and yeah. Okay, so problem solved then. Maybe. So, did this solve any problems? Yes and no. It does solve one problem. Well, servlet container threads are released, so they can serve other incoming requests. But we do have now, for each of these backend services, we have a separate thread pool, right? So, and that operation inside that thread pool is still blocking. We might not be able to change that because we are using some third-party library given to us by the vendor of backends. But clearly, this thread pool might overflow, right? So we have to take care of this then. So what do we need to solve this problem? Because we had one problem, we have partly solved it, but now we have another problem. So we need all kinds of management of thread pools. We have separate thread pools now for all the backend services. So we would need monitoring of these pools, all kinds of statistics, latency of execution, how many tasks have been executed, blah, blah, blah. All kinds of rejection policies. You could say that if one thread pool is already full, then we could reject incoming tasks right away, right? And of course, you'd have to size the pools properly, which is a science of itself. So, as you might have guessed, one part of the puzzle was Servlet 3. The other part is Hystrix. Because Hystrix, it's an open source library made by Netflix. It gives us all of these things and a lot more. It is a library for command isolation so that you can protect your distributed system from high latencies, network failures, etc. It's quite elegant. It's very easy to run commands in separate thread pools, set up rejection policies, etc., and then gracefully degrade when things are not going so well. It has wonderful monitoring tools. You see this. This is the monitoring from Hystrix. It shows 1, 2, 3, 4, 5, 6 thread pools. Gives us all kinds of statistics, how it's going, etc., etc. So, okay. So, you have two parts that fit very well together, Hystrix and the Servlet 3 API. Okay, so let's try this out then, because I wrote an integration then between Hystrix and Servlet 3. It's on GitHub. You will see the URL later. But let's just try this then. Let's find let's just go to. This is a very simple web application. So let's have a look at this first. Can you see this? Yeah, maybe. Yeah. So this is a web XML file. It shows one simple servlet called foo-servlet. It is mapped to /foo. The foo-servlet is, excuse me, it's here. As you saw in the slides, this instantiates a very slow service. It calls a blocking operation towards this, which returns a string, sets the content type, and writes it back. The very slow service is obviously just a mock. So it's like this. It just returns a string response from very slow remote service called from thread and the thread name. So, okay, let's just try this so we can see that it actually works. Okay, let's start it. Yeah, there it is. Response from very slow service, called from thread, QTP, blah, 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 blah. This is just a Jetty thread, right? A servlet container thread. So, fine. That works then. So, how would I use Hystrix-Servlet to run this in a separate thread pool? So, first of all, I would have to add the dependency in the POM. It's right here, Hystrix-Servlet version 1.0.11. Then I would add a separate class next to the foo servlet, which I have called async foo servlet. This needs to be annotated with the web servlet async supported equals true annotation. This is a servlet 3 annotation. It needs to extend async wrapper servlet, which is provided by the Hystrix-Servlet API. And then, quite simply, it instantiates a foo servlet and gives that to the superclass. Now what you do is go into your web XML, and let's change this so that we are creating an async foo servlet instead. We can leave the rest as is. The name can stay foo servlet like this. Okay. Let's stop this and run again. And let's see. Okay. So now, this servlet was not executed by the servlet container thread. It was executed by a Hystrix thread. I can tell you as much about how Hystrix names its threads in the thread pool. So this is in a thread pool called default, since it's called Hystrix default 11. So, we are running this in one separate thread pool. So why was this called default, and how did this help us? So, imagine then in the common case is that you are receiving a request. You can, based on that request and some configuration and things that you already know, you can find out what thread pool this should execute within, because you'll be needing more than one, right? So let's try to do that. You go back to your original servlet. This could then implement Hystrix aware servlet, because that is provided by the Hystrix-Servlet API. Let's implement a method here. It's called get command group key, a command group key. That's Hystrix speak for thread pool name, really. So let's see here. We have the request, which we need to determine what thread pool to execute within. And since this is our original servlet, we already have all kinds of knowledge, probably connection to a config database or whatever. So let's see if request get parameter blah parameter okay. In your application, this would obviously be a bit more advanced, but let's just say that if we receive a request with the parameter blah, which is true, then return blah. Otherwise, we'll return foo. Okay? So let's try again. Okay, so the same request should now execute within foo, right? Okay? And another request, which we know goes towards backend blah. Blah. Okay. So that request would go towards thread pool blah, and the other one goes towards foo. So we can use this to separate our requests into various thread pools. And we can also, I haven't set up monitoring for this talk, but as you saw in the slides, Hystrix has very good monitoring capabilities. So you can see then in the monitoring that, okay, this thread pool blah has executed this many tasks and the other one has executed this many tasks. The latency average is this bad, etc., etc. There are other things you can tune in the async wrapper servlet that you provided. You can also set the timeout for the tasks you are scheduling. So let's say that if the backend service takes longer than 5 seconds to respond, then you just want to reject that. Yeah, I mean, you're basically just returning a default response instead, for instance. And you can also set the pool size, etc., etc. So, let's see. Okay, so to summarize, you can customize which thread pool you want your request to execute within. So the slide is a bit wrong. You can decide that on a per request basis, not per servlet. You can obviously set the pool size and the timeout for the pool. There are various hooks to execute code in here. You can have code executed when you're using this framework by the servlet container thread before passing things to Hystrix. Or you can have code executed before, by the Hystrix thread before executing your original servlet. And also the same after execution. We're using this, for instance, for some thread local state that was set by a web filter, which we needed to hand over to the Hystrix thread and then clear it afterwards. If you can avoid thread locals, that would be better, but sometimes they're needed. And obviously, since these are two asynchronous APIs, there are callbacks for all kinds of things like timeouts, errors, and completions from both the Servlet API and the Hystrix API. So you can have hooks executed in response to all those events. Yeah, so clearly this won't fit everything. There are some limitations or some cases where you would be better off not using it. In some cases, it would be a much better idea to push Hystrix further down the stack. So what does that mean? It means that in my example here, we could know from the request which thread pool to execute within, right? Well, can you always know that? Let's just say that you're getting a request and it goes towards backend A. Okay, fine. Put that in thread pool A. You're getting another request and actually you don't know yet. It could be going towards thread pool A, B, C, and D. So what do? You could create a new thread pool for A, B, C, D, but that kind of explodes so with all the permutations of all your backends. That would be a gazillion thread pools, right? So you could just add it to thread pool A then. Yeah, it would work. But then again, you could be polluting that thread pool. There is no longer any command separation. If you have loads of requests going for backends A, B, C, and D added to thread pool A, then a service disruption on C might affect all the tasks in that pool, even the ones that are only going towards A, right? And that was what you wanted to avoid in the first place. So in this case, it would be better to just use Hystrix directly and push that all the way down the stack. So that you would be modifying your servlet to begin with. The reason we did not do this initially, at least, was that we have so many backends, as I noted initially. We have at least 30 in daily use. So, and they need to be inside one web application. So, changing all this plugin code in our code base would be way too much work, and we can mostly know which thread pool to execute within up front. So this was a good way to do it. So yeah, we have 3 or 4 minutes in case there are any questions. Yes?
You said you have 30 or something backends.
Mm?
For some of them, are you able to use non-blocking I/O towards the backend service, or always just this blocking I/O?
Well, that depends, because the question, if you didn't hear it, could we use non-blocking I/O towards any of the backends? Probably some, yes. But many of them are, the communication is done in a way that the vendor is just giving us a jar file and we have to use it. And if that code uses blocking I/O, then so be it. But on others, we are in charge of all the code ourselves, so we could use non-blocking I/O. Yes. Anyone else? Okay. So if you wanna check this out, this is the URL to the project on GitHub, and that's my email address. So thank you.